Hello there. In this video, we try to classify different signals based on their characteristics. First, we will divide signals into continuous time signals and discrete time signals. A continuous time signal x of t is specified for a continuous set of time instants t, which means the time is a continuous variable. However, a discrete time signal, which can be a sampled signal, x of t, is specified only at discrete time instance t, which means that the time variable is discrete. For example, this sinusoidal signal is a continuous time signal. Notice that this time here is continuous. So we have a value for x of t at 0 time. We have a value for x of t at 1 second, at 2 second, at 3 second, 4 second, maybe 1.1 second, maybe 3.5545 seconds, and so on. So for all instants of time in this continuous time axis, we have values for x of t. This is different than this discrete signal. Notice that this discrete signal has a value at this point in time, but nothing here. And then it has a value here, which we typically call sample, and then nothing here. And then the signal has a value here, and then nothing here, and then value here, and so on, which means time is discrete, and we only have values at discrete time instants. Here is another example of a continuous time signal. Notice we have for all those times, we have values for x of t. We call this continuous time signal. However, here we only have samples of the signal at certain discrete times. We don't define the signal for every possible instant of time. And a lot of cases, instead of writing actual time here like 1.5 second or 2 second, we use an integer number to represent that this is sample number 0, this is sample number 1, sample number 2, sample number 3, and so on and so forth. A lot of times, discrete time signals are expressed as a sequence of numbers denoted by x of n. So instead of saying x of t, we say x of n to indicate that this is discrete where n is an integer. Sometimes we use the set of x sub n also to represent the discrete sequence, which means a discrete time signal. And we keep x of t to represent the continuous time signal. A lot of times, students confuse the continuous time signal versus discrete time signal with a different concept called analog signal versus digital signal. But those concepts are quite different, as I'm going to explain shortly. But before I go into analog versus digital, a few words about discrete time signals. A discrete time signal x of n may represent an inherently discrete phenomenon, like the number of students registered for this class every semester. So we could have a phenomenon that is discrete by nature. However, most often, x of n is obtained by sampling a continuous time signal x of t. And we call those discrete points that we obtain from the continuous signal samples of the continuous signal. So we take x of t, but at point t naught. And then we take another sample x of t, but at time, say, t1. And then we take another sample at time t2, and so on and so forth. And we call those the discrete values x of 0, x of 1, x of 2, x of n, and so on. So in a lot of cases, the discrete time signal is actually a continuous time signal that is sampled. We will talk about sampling theory at a later point in time in this lecture series. If we do sampling, we'll write x of n or x of sub n equal x at time tn. And if the sampling interval or the sampling time, which I'm going to call ts, ts is the time between the successive samples. If that time is constant equal to ts, then we can write xn or x sub n is equal x at time nts. So the first sample at 0, and then the next sample is at 1 multiplied by ts, and then the next sample is at 2 times ts, and then 3 times ts, and 4 times ts, and so on. That's why the index starts at 0, 1, 2, 3, 4, and so on. That's the index n. Next, analog versus digital signals. What do I mean when I say analog signal or digital signal? Analog signal x of t is a continuous time signal that can assume any value within a continuous interval between a and b. So if x of t is continuous time and also continuous value within a certain region, which could be, by the way, minus infinity to infinity, we call it analog signal. This is an example of an analog signal. Notice that not only the time is continuous, but also the values or the vertical axis is also continuous, which means I could have any value here within a certain region, maybe minimum A up to a maximum of B. So this value could be 1 volt, 1.2 volt, 1.25 volt, or 1.55555 volt. Any continuous value within a certain region, or maybe from minus infinity to infinity, means that your signal is analog. A lot of signals that come from nature are inherently analog. This is different than digital, because for digital signal x of t, even though it's continuous time, it can only assume a finite number of discrete values. If you are talking about a binary system, then you are limited to only 2 possible levels. Sometimes in Emery systems, we could go higher number of levels. Say m equal 4, I'm allowed 4 levels. Or m equal 8, I'm allowed 8 levels. See here, this is a digital signal. Notice that in terms of voltage or in terms of x of t values, I only limited myself to this value and this value. Maybe 5 volt and 0 volt. Maybe this is TTL logic. So I'm not allowed to send, for example, 2 volt or 3 volt. I'm only allowed to send 5 volt or 0 volt. This is different than this signal, which is analog, because this analog signal can assume any value in that continuous region. But this one here can only assume 2 possibilities. If you are limited in terms of x of t values, we call this digital signal. Even though the time is continuous, still the time is continuous, not discrete, but you are limited in terms of values. We call this digital, unlike analog, where you are not limited in terms of values within, of course, a certain region. So to summarize, continuous time versus discrete time refers to the time or the horizontal axis. Is time continuous or is time discrete? However, analog versus digital refers to the signal amplitude or value or voltage on the vertical axis. Are you limited to a finite number of possibilities, maybe 2, maybe 4, maybe 8, or you are not limited to a certain number, you have a continuous region of values? Then that's analog. Please notice that I did not mention discrete time signals, because typically the discrete time signal is the intermediate stage between converting the signal from analog to digital. If we want to convert analog to digital, the first thing we do is sampling, where we convert the continuous time signal into discrete time signal. But I'll keep sampling, which is an important topic for a later lecture. The next classification is real versus complex signals. A real signal, x of t, has all values represented as real numbers. However, a complex signal, the values of x of t can be complex numbers. Remember, however, that a complex number can be a purely real number, a purely imaginary number, or a combination of real and imaginary values, so a plus jb. So strictly speaking, the complex function is the more general case, and the real signal is a special case of the complex function, where all the complex numbers are real numbers. However, we'll make a distinction, because in real life, the physical quantities we can measure, we can see in the lab, are actually real functions, and they are never complex signals. So you might be wondering, why am I telling you about complex functions? The reason is that they represent very nice mathematical tools that will help us solve certain mathematical problems way easier. Like, for example, this function, e to j omega t, you know from Euler's identity, it is cosine omega t plus j sine omega t. If I start using the cosine, which is a real value, a real function, a real signal, the solution is a little bit more difficult. However, if I switch to e to j omega t, which by the way has the cosine built in, but it's a more general complex function, then I simplify a little bit the Fourier series calculation, and that's exactly why we are going to deal with complex signals, even though they do not exist in real life. How about deterministic versus random signals? A deterministic signal x of t has its description well known either in mathematical form or a graphical form. I'll give you some examples. X of t equal a cosine omega t. Notice that x of t here is deterministic because I could describe it using an equation. Once you can describe your x of t using an equation, then you completely describe x of t for any point in time. If I say substitute t here 1 second and calculate x of t, you will be able to draw x of t for time equal 1 second. If I say give me x of t after 1 hour, you'll substitute here t 1 hour, which is 60 minutes multiplied by 60 seconds, and then you get what x of t is. If I say predict what x of t is going to be next year, then you can substitute the value of time, 365 days multiplied by 24 hours multiplied by and so on until you get the value of x of t, and then you can draw x of t for any value. A similar deterministic signal is a sine omega t, which you can see here. I use the equation a sine omega t to draw current values, future values, past values. I can tell what is the value going to be at any point in time because I know the equation. Another example is this signal, which you're familiar with. So a homework for you is to try to draw a rect t over tau, and you will see you know all the values for that signal at any point in time. This is different than a random signal, where the values of x of t at any given time are random values, similar to flipping a coin. In that case, the random signal x of t cannot be modeled using an equation. Rather, it is characterized using probability theory. An example I'm going to show you is noise. This signal is common in communication systems. It is extra noise that comes into our channel, and noise does not have an equation, unfortunately. It's more like flipping coins. I say to you, all right, I'm going to flip a coin. Is it going to be heads or tails? You say, I am not sure. I have to see the experiment first. I have a feeling, maybe 50% chance it will be heads, 50% chance it will be tails. Same thing you can say about this random signal, which represents noise. I say, what is noise going to be at this point in time? And you say, I'm not sure. I have a feeling that it will be positive with 50% chance. I have a feeling it will be negative with 50% chance. I have a feeling it will be around 1.1 volt with a certain probability, and so on. This is what we call random signal. In this lecture series, I'm going to look at only deterministic signals, but we have a separate course for random signals, so I'm not going to talk about them here. All right, periodic versus aperiodic signals. For the signal x of t to be called periodic with period capital T, we must have a positive non-zero value of t for which we satisfy this function. X of t plus the period t must be equal to x of t for all times, which means that the signal keeps repeating itself every period t. Notice that at this point in time there is a value for the signal, but then after the period t I have the same exact value. If I have another time here after a period of t, I repeat myself. So if the signal keeps repeating itself every period t, we call this signal periodic function or periodic signal. This is an example periodic signal. Notice after this time, the function repeats itself again, and then repeats itself again, and then repeats itself again, and so on and so forth. Same thing here. This triangle repeats itself again and again and again. Some people would say the period is t naught. Some people will say the period is 2t naught because the function repeats itself after 2t naught. Some people will say the period is 3t naught because the function repeats itself after 3t naught. And all those values satisfy this equation. However, we will only pick the smallest positive value that satisfies the above equation, and I'm going to call it the fundamental period t naught. When people talk about period, even though there are many definitions, the most common definition, the one that is used 99% of the time, is the fundamental period, which is the minimum possible period. And I'm going to call it t naught so you'd remember this is the fundamental period. In my example, this is the fundamental period. In this example, this is the fundamental period. So please don't tell me that this is the period. Even though mathematically speaking, it can be called the period. From now on, when I say period, I mean fundamental period. That's why I'm going to use t naught to always remind you to take the smallest positive integer. That satisfies this equation. Some more examples. This sinusoidal signal also repeats itself. In this case, this is the fundamental period. This is the fundamental period. Or you could start from this point. This is the fundamental period. Or you could start from this point. This is the fundamental period. In all those cases, it is equal T0. Same thing here. This is repeated triangular signal. This is the fundamental period. This interval T0 is the fundamental period. Again, the smallest positive value that satisfies the above equation is called the fundamental period T0. Typically, we use the word period to mean the fundamental period. On the other hand, if x of t does not satisfy the above equation, it is called non-periodic or aperiodic signal. Aperiodic signal. Aperiodic signals do not repeat themselves, so they do not have a fundamental period. I'll give you examples of aperiodic signals. Remember the single rectangular pulse? It's aperiodic. Notice it does not repeat itself. The sawtooth pulse, it does not repeat itself. Notice I don't have repeat here. So this is one single sawtooth pulse. It does not repeat itself. We call it non-periodic or more commonly aperiodic. Here is another signal that is aperiodic. By the way, noise, which is random, does not repeat itself. I know it goes from minus infinity to infinity just like periodic signals, but it does not repeat itself. That's why it's aperiodic. The noise signal is aperiodic signal. There is one special case. Sometimes I get asked about it, the DC signal or the constant value. Is it periodic or aperiodic? Well, the DC signal or the constant value is quite a special case because the condition x of t plus t is actually equal x of t, and this applies for many values of t. But we do not have the smallest possible t, which is called the fundamental period T0. So is the DC signal periodic or aperiodic? Well, I don't really care. You could call it periodic, you could call it aperiodic. For me, it's just a very special case. We call it the DC signal or the DC value or the constant value, and we know what it looks like. But in terms of Fourier series, we typically give it zero frequency. We'll talk about this later, God willing. Something to keep in mind, a nice property of periodic signals x of t is that when you're doing an integral over the fundamental period T0, you have some flexibility because the area under x of t over an interval of duration T0 is the same no matter where you start. For example, if I have this x of t and I say to you guys, let's do the integral of x of t, find the area under this periodic signal from time 0 to time T0 over this period, from time 0 to the period, in this case, 2 seconds. You could do the integral from 0 to 2 where you find the area of this triangle and find the area of this triangle. But someone else might decide, well, let me do the integral from minus T0 over 2 to T0 over 2. So I'm going to start at this point, minus T0 over 2, and I'm going to end at this point over one period. Can I do that? Yes, and you will find the same integral, the same area, because you'll get this positive triangle first, but then you'll get this negative triangle second, and you'll get the same answer. What if I start at minus T0 over 4 and I end at a 3 T0 over 4, which is one interval of T0? You'll also get the same answer. What if I start at a certain point and I end up at another point after T0? Would I get the same answer? Absolutely yes. That's why a lot of times I just write the integral over one period. Pick whatever starting point you want, end at a point after exactly T0, you'll get the same integral. This is a nice property we will use to our advantage to simplify calculating integrals in Fourier series. Next, what is the frequency of the periodic signal? Remember I told you when we talked about the cosine, we have two ways to define frequency. We have hertz and we have radian per second. The ordinary frequency and the angular frequency. The ordinary frequency is 1 over the fundamental period, 1 over T0, and you get hertz. However, the angular frequency is 2 by f, so it is 2 pi over T0, and you get it in radian per second. So the frequency is 1 over T0, that's hertz, or 2 pi over T0, that's radian per second. However, since I'm using the fundamental period, I want you to use the name fundamental frequency. Instead of using the general word frequency, remember to use the fundamental frequency. I'm going to give it the symbol F0. F0 is 1 over T0. We say the fundamental frequency of the periodic signal, F0 is 1 over T0. Or if we want the angular fundamental frequency, then it's 2 pi over T0. Why am I going to use F0 omega naught? Why being specific and saying fundamental frequency, not just frequency? Well, there is a reason, and that is the periodic signal turns out not to have a single frequency, it has multiple frequencies. That's because it is composed of multiple harmonics, and each harmonic has its own frequency. It turns out that the fundamental frequency F0 is the frequency of the first harmonic, which I'm going to call F1. So F1 is only the first harmonic, and that is equal to the frequency of F0, or the fundamental frequency. But if you go to the second harmonic, the frequency is not F0. It will turn out to be 2F0. While the frequency of the third harmonic is a 3F0, and the frequency of the fourth harmonic 4F0, 5F0, 6F0, and so on. That's why I want you to be careful. If you just say frequency, I'm not sure which one you're talking about. First harmonic, second harmonic, third harmonic. But if you say fundamental frequency, I know that you are talking about the frequency of the first harmonic, and we say it's also the frequency of the periodic signal. So to recap, the fundamental frequency is the frequency of the periodic signal, and it's the frequency of the first harmonic in the periodic signal. Other harmonics have frequencies that are multiples of the fundamental frequency, where the fundamental frequency F0 is 1 over the fundamental period T0. I say the same thing, by the way, for angular frequency. Omega n, the nth harmonic, has a frequency omega n is equal to n by omega naught, where omega naught is the fundamental frequency in radian per second. How about discrete time signals? Periodic discrete time signals x of n satisfy for a certain positive integer n, x of n plus n equal x of n for all n, and that integer n replaces the period. The fundamental period n0, we say, of x of n is the smallest positive integer n for which the above equation holds. So for this example, see here, the signal repeats itself after a certain number of samples, after a certain n. So I'll leave this as a homework for you. Give me what is n for this periodic discrete time signal. Put x of 0 here, and then tell me what is the next x of n plus n that is equal exactly to x of 0. And this way you can figure out capital N, the fundamental period. Some concluding remarks. A sequence or discrete time signal obtained by uniform sampling of a periodic continuous time signal might not be periodic. Even though the continuous time signal is periodic, and then you sample it, you don't get periodic sequence. How can this happen? Please think about it. Think about a condition where this does not happen, and I'll give you a hint. Think about the relationship between the fundamental period T0 of the continuous time signal and the sampling time Ts that you need to go from continuous time signal into discrete time signal. What should the relationship between T0 and Ts be so you don't get periodic sequence from periodic signal? Another thing to keep in mind, the sum of two continuous time periodic signals may not always be periodic. Sometimes it's periodic, sometimes it's not. Can you tell me why? What conditions make it periodic? What conditions make it aperiodic? The sum of two periodic sequences is always periodic. There are no conditions that will allow two periodic sequences to be added and not give you periodic sequence. Let's stop here. In the next part, we'll continue classifying signals into odd and even signals and energy and power signals. If you have questions, leave them please in the comment section. Take care.